let's get going with lecture for today. We've just given you the exam printouts, and I want to talk about them for just a few minutes. If you look at the very top right of your printout, there is a percentage up there you can ignore, because that's a percentage based on 46, but our exam is a 50-point test, and it doesn't have any of the clicker points. I have all the clicker points, and I have your Scantron. So the only thing on the top is the total score and the raw points in the upper right part of the printout. If you look at your printout, you can see which question you answered correct and which one you answered incorrect. The answer key is, I believe, the second column. Is that right? Answer key is the second column. So you can compare your answer to the correct bubble or the correct dot, but that doesn't really help you very much. I have something prepared for you, however, that will help you. But before we go any further than that, I'd like you to also take a look at the very top, a little bit more towards the middle. It says exam form or test form, I think. And you'll be able to see A, B, C, D, or E. All right? Or A, B, C, or D in there. Okay? So that is your test form. It's recorded by the system. And it is going to be useful for you because of the exam blurbs. And I want to show you a little bit about the exam blurbs that I've produced for you so that you can know what your printout says. All right? Now, if all you have is that printout, you just know, well, I got number 7 wrong. And it's option B or something like that. But it doesn't really tell you what the question is about. The blurb files do. Now, the blurb file is a PDF in web courses. It's key to each test form. Here's what the true-false part of the, at least the first 4 items of the blurb look like. I think this is for Form A. And so it tells you that number 9 in Form A was about stopping time and stopping force. It doesn't give you the verbatim question, but it does give you a short blurb, as I phrase it, that tells you the basic topic of each question, including the ones that you get wrong. All right, so number 10 is initial conditions. Number 11 is definition of Newton in terms of fundamental units, etc., etc. Now, the only ones that don't have a blurb are the matching ones. All right, those are the first, I don't know, I think it's the first 7, no, the first 8 questions on the test are matching. For some reason, it doesn't generate a blurb about them, but otherwise it does. All right. Now, those blurbs combined with your printouts are a very nice study tool for the final exam. Now, almost everybody in here is going to be taking the final. Maybe a few of you, if you get good exams scores for exam 1 and exam 2, you will be permitted to skip the final. But otherwise, you'll be at the final, and you want to be able to review. And the printout that you now have and the blurb file, which you can download, it's a PDF. It's linked to a page in web courses. Those together will make a nice review study tool. All right. So definitely keep those babies. Another thing, I don't have a slide about it, but I could tell you that the performance for both sections was fairly good. It was average was about 76% clicking and Scantron put together. So that's pretty good. I usually try to get something in this. I usually try to get a little about 70% or so. All right. Now 76 would actually be a B minus or a B, because I don't give pluses and minuses. So that's pretty good on average. A little bit higher than usual, sometimes, especially for exam one. Now, sometimes the exams, might be 69%, for another exam, a little tougher. But usually the average is going to be around 70-something percent. And this one came in pretty good. All right. Another thing that I want to talk about is clicking, but before we continue, I want you to ask a question about your Scantron printout if you have a question. Yes?
What was number 9's answer for A?
Dude, just look it up on the blurb file. Yeah, I did, but I'm not going back. What?
So that was my question.
It depends on which form you have.
Yeah, that was Form A. That was Form B.
Yeah, it might have been whatever it was, Form B or Form A. But just look at the blurb file when you get it. All right. Just check it out. That's why I mentioned that you have, at kind of in the middle, it says the test form. Then go download the blurb file for that test form, and you'll see. All right. Another question. Oh, one more thing. I want you to look at your printout really carefully and see if you have any questions where it says you have two answers, because that will be marked incorrect. Also, look at the whole list of all 46 items and see if one of them is marked blank. All right, raise your hand if you have a double answer anywhere on your test. Okay, good. Raise your hand if you have a blank somewhere on your test, on your printout. You have a blank?
Yeah.
You do? What's your name again? Deandra. Wilson. Watson. Winston. Okay, close. Okay. Deandra, I want you to give, can you bring that up to Miss Darian and she'll fix that up for you. And you can look at the Scantrons are in here. We'll get anybody else with a blank. Okay, bring that up here. You guys bring those up and Miss Darian will verify that. All right, and return to your chair and she'll be doing it while we're lecturing. And you can pick it up at the end of class, okay? And what we'll do, Deandra, and the rest of you guys, we'll see if you really do have a blank or if you bubbled in an answer that was a little bit light. And there was a student in the first class that didn't get a single answer on his test because every single dot on his Scantron was too light. So we're going to have to grade that one by hand. Okay. Now, I want to talk about the iClicker 2 items for just a minute. Now, this is a screen grab of the grades page. You have 3 Exam 1 scores, clicking and Scantron, and then the total of the 2, all right, whatever that works out to be. And the Scantron is embargoed right now. I'll unlock that for you after class. Okay, now that everybody's, I usually have that on mute until I hand back printouts. All right. Anyways, Exam 1 clicking is important because this one you can get partial credit. And I want to show you how I give partial credit. For instance, so this number over here on this row of your grades page might contain partial credit. So if your grades page has 1 point, then that's partial credit for 1 question. A 2-point question, you got 1 point. Or the brain burner, you got 1 point out of 3. Okay? And so I want to go through some examples of that with you, and so that you can see how I grade things and how I spot answers that you've typed in with your iClicker that might justify partial credit. All right? Now, one of the questions was the drop distance at the stadium. Here's a close-up of a spreadsheet that I have And basically what I do is I sort the column, I sort based on the answer column. And so 30.6 is somebody's answer, negative 30.6. And of course, the correct answer for at the stadium, problem 1, was 30.6 meters. And so this student had a minus sign in there, and that is partial credit, 1 point instead of 2 for that particular student. All right. Now, another example is the brain burner. Here's another close-up of the spreadsheet. And this student here that had it typed in equals 31.3. Actually, 31.3 is the VIY for the brain burner. That was, and many of you got it. And this student, I said, all right, they accidentally typed in the equal sign and then 31.3. So we'll give it 3 points on that one. So that one is not partial, it's full points. And I can do that with the iClicker. So if I see you, a little bit flailing or something, or like a typo like this, I could say, all right, I'll give it to him. Which is what you do when you're grading a paper test, a written test, which you can't do it very well in a class this size. But with this, with the iClickers, yes, you can. So it works out pretty nice. Here's another example, the coin stopping time, for which the correct answer was 1.85 seconds. And I decided, okay, I guess this guy wasn't wearing his X-ray specs. He thought that S was a 5. I'll give it to him. All right? Out of the goodness of my heart. So that guy got another case, not partial, but full points, based on me eyeballing the students' work. Okay, now, here's another one. This was from the brain burner answer column. And this student, for the VIY, typed in 3.19. Now, this answer here is a nice number. It is an intermediate answer or an intermediate value. That's delta t. That's the rise time or the drop time. So that is actually a legitimate number, but not the actual answer. So I gave that person 1 point out of 3. All right, so that may be you. All right, and I'm able to do this with all the iClicker questions, at least the ones that are numeric. And sometimes every once in a while, I'll put a multiple choice that's really appropriate on the iClicker part. Then it's A, B, C, or D. That's like a Scantron. But if you're typing in a number, I can definitely eyeball it and see if it deserves full credit or partial credit or no credit. Right? And so now, questions about any of this? Okay, let's keep going. I want to talk about the participation data roundup that I did yesterday. And I saw a couple students asking about it in discussions. What I did was put 2 new lines in the grade book, or in the grades page. And I posted it yesterday, February 8th. So it's labeled 0208, and then the word summary, comma, answers. And that tells me how many clicker questions you've answered, or that tells you how many you answered in the 2 lectures that we had last week. January 31st and February 2nd, those were the 2 lectures for participation pointage for the semester. And then we're going to have some today, okay? And that'll be on the next roundup. But this roundup was just 2 lectures worth. Eventually we'll have all the lectures in the roundup. Here's the other number, 0208 summary. This is the number of questions you may have correct. So in this particular example, the student has 7 out of the 11 correct. Now, as I mentioned before, that's not a participation grade, but it does give you a bonus point 4 bonus points at the end of the semester if that number is 75% or higher of all the questions that we've answered. Now, right now, we've got 11 points or 11 questions on the books last week. January 31st, last Tuesday, and February 2nd, last Thursday. All right, so it's no great shakes right now, but by the end of the semester, we're going to have over 100 most likely. So whatever this number is over here, you want to have 85% of that covered. All right, and if you do, you'll get 25 out of 25 on your for your semester grade. For the participation part, 10% of your semester grade. All right. And I'll be doing updates, not every day, not every week, but maybe 3 or 4 more times this semester, every 2-3 weeks maybe. Okay. So this is the first one, and it's good. Any questions about participation pointage and so forth? Okay, let's keep going. Take out your clicker, and let's answer a clicker question.
Is it multiple choice?
It is. Okay, turn on your clicker. And here's your question. It's multiple choice, and it's kind of a brain burner. I want you to really think about this. An object is accelerated, but it never speeds up and it never slows down. What kind of acceleration is it? Now, if you've done a little bit of reading, you know the answer to that. Okay, 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, go ahead and display this. Now, there's a wide range of answers here, fairly well distributed in all the, and actually the least popular one is the correct one, sideways. Go ahead back to the display. And we're going to be talking about the sideways acceleration in today's lecture. This is what we would call a centripetal acceleration toward the inside of a curved trajectory. And so what we're going to do is continue Sir Isaac Newton's development that he wrote in the Principia, the Mathematical Principles of Natural Philosophy. And we're going to study uniform circular motion. And here is a circle. So go ahead and sketch a circle. And I've got an object on the circle, and I have a dotted line for the radius that goes from the center of the circle directly to the object itself. So this is like, it's actually like, it doesn't have an arrow, but it's like a position arrow. Okay? Now, in uniform circular motion, let me animate this now. Go ahead and take a look at this. Here it comes. All right, I'm going around clockwise. And uniform circular motion is like that. It has a constant speed, but it's always changing. It's not speeding up or slowing down. Many of our communication satellites have uniform circular orbits. Now, some of our spacecraft don't. They have slightly elliptical orbits, okay, like the space station and stuff, different spy satellites and stuff. But the communication satellites are usually very, very close, if not exactly circular. We're going to talk about that today. So we're going to get back to chapter 3 and just wrap this up. Here's a diagram from that chapter. And It's around page 49 and so forth. And if you look in that chapter 3-6, around page 49 and so forth, you see a bunch of triangles. Now, this red one up here is what I call the velocity triangle, and this one down here is the position triangle. Now, the dashed line that you saw on the previous slide, that where the blue square went around, actually it went around in a clockwise manner. That dashed line on that diagram is the same as these ones marked R for position triangles. The base of that one is just the line segment between the two radii, the ends of each radii, of each radius. Then the velocity triangle up here, these are the two velocity states at different points. Now, if you've read that part of chapter 3, you'll know what I'm talking about. And the interesting thing about this, what I'd like to emphasize, is that looking at the geometry allows us to figure out that there are proportional triangles. Okay, these two triangles, the velocity triangle and the position triangle, they're proportional. All right? The acute angle in each triangle is the same size. They're isosceles triangles. And therefore, you have side angle side similarity. All right? They're not the same size, but they are similar. From that similar triangle or proportional triangle concept of geometry, we're going to get a dynamical concept, the formula for centripetal acceleration, the acceleration toward the center. Now, here's an equation that expresses the proportional triangles. Okay? And over here, the top of each is the short side of each triangle. So this left-hand ratio, V delta T over R, that's V delta T is the short side of the position triangle, because delta X is equal to V delta T. Pretty close, all right? And then the numerator of the second ratio in the proportion, delta V, and the second ratio is delta V over V. Delta V is the short side of the velocity triangle. All right? So the numerators in this proportion are short side and short side. And then the denominators are isosceles side and isosceles side for the other triangle. All right? So make a note of that. All right? So the ratio between, if the two triangles are proportional, the same shape, then this ratio, whatever it happens to be, it could be 2.75 or something like that, it's going to be the same ratio for both triangles. All right? And this quotient here on the right, that's the velocity triangle quotient. And this one over on the left is the position triangle quotient. And they're equal. And we know that from the design, from knowing two things, that the trajectory is circular and that it's uniform speed. Okay, so the V doesn't change. The length of the arrow doesn't change, but the direction changes. All right? Now, if you rearrange this, if you take this V in the denominator of the right side, look at it now. See this V up here in the denominator of the right side? If you cross multiply that over to the top of the left side, you'll have a V squared. If you take this R over here and leave it there, and then take the delta T from the numerator and cross multiply it to the bottom of the right side, you get delta V over delta T. I should have given you a clicker question. What's delta V over delta T? What's that the definition of? Acceleration, yeah. So really, if you bring the v squared over to the left and the delta t over here to the bottom on the right, you've got v squared over r and a delta v over delta t. That's an acceleration, and that is the centripetal acceleration of this object, whatever it happens to be. And we give it a subscript c. It is the acceleration toward the inside of the circle. It's always, if it's curving left, the delta v is to the left. If it's curving, if it's curving right, then the delta v is to the right. Okay? All right, so it's always toward the center. Here's a visual summary of it. There's a circular path. And if we say that the speed is constant, so this yellow tennis ball is going around in the circle at 10 miles an hour, so it's speedometer, it's on cruise control at 10 miles an hour. Okay? So v is the same, but it's changing its velocity vector because it's changing direction continuously. And that acceleration vector is directly toward the center. Right? And you can read more about that in chapter 3.6 of the ebook. Here's the radius of the circle. Right? And so the centripetal acceleration, how much delta v over delta t have you got? Well, it's not changing the speedometer, but it is changing the direction, and that counts as an acceleration. If you get bumped to the side without changing your speed, that means you've got accelerated. Somebody had to bump you to do it. All right, same thing here. Now, if you think about this on a circular track, then, like I mentioned in the textbook, you have to have tires that have some grip to them, and then it's actually the friction force from the track that gives you newtons of force and then an acceleration toward the center. Now, you control the velocity, or you control the speed with the gas pedal and with the brakes. All right? So if you're driving around a circle like the Nardo Ring down in the southern boot of Italy, that big, great circular shaped track, you can go on any speed. It just depends on how much gas you put on. If you want to slow down, you hit the brakes a little bit, and you can still stay on the Nardo Ring. Now, the other thing about it is the radius of turning depends on what the design of the track is. All right. Now, if you go over to Daytona Super Speedway or whatever it's called, they have very exact specs for the radius of turn 1, turn 2, and then turn 3. All right, and you can look it up. All right, so any kind of a circular track, when they're building it, the architect and the engineers, they're gonna say, all right, let's give this one a radius of 110 meters. All right, and then they also at Daytona. Who's ever been to Daytona? Do they bank the turns at Daytona? Okay, so the turns are. I've never been. I'd like to go there one of these days, except it's really loud, isn't it? I mean. See, I wouldn't like that, but maybe I'll go. You got to take off. What's that? Yeah, I could wear earplugs, I guess. Anyways, so the design of the track, that gives you the R. And, every road that you see that's well designed, and, any road that is constructed by an engineer and an architect is going to have a radius of turning. Now, if you're out in the wilderness or something, and you're on an old wagon trail that was formed by horses and wagons and stuff in the 1890s or something, heading for Oregon or something like that, then you might not have a precise radius. But any kind of roadway you see around here definitely is going to have it. Now, so let's just do a little summary here. We had proportional triangles, velocity triangle, position triangle. That little squiggle between the two phrases, velocity triangle, position triangle, that squiggle means similar to. So if the two triangles are similar or proportional, then that means they don't necessarily have the same sizes and dimensions, but they have the same shape. And therefore, if you make a ratio of short to long or base to isosceles, it's going to be the same for both triangles. And that similarity geometrically can be interpreted, if it's uniform circular motion, as the centripetal acceleration. Now, Sir Isaac Newton's second law, F equals ma, just attaches an m to whatever is being accelerated. So the centripetal force is mv squared over r. Okay, that's just F equals ma with v squared over r being your a. And we're going to apply this in a second to the whole idea of acceleration and gravity. And it's actually kind of interesting what Sir Isaac Newton pulled off. Now, let me pause for questions before we continue. Okay, let's keep going. All right. Now, what we're going to be talking about is Sir Isaac Newton and his friend Edmund Halley. Let's start out with Sir Isaac Newton. What he was intrigued with was the relationship between terrestrial gravity, the proverbial apple that fell onto his head, and the force that kept the moon, which he figured was the same force, the force of gravity that keeps the moon in place on its orbit. So he could get a decent measurement of g, the terrestrial acceleration, basically doing distances and times. And he could also estimate the centripetal acceleration of the moon on its orbit. Now, how can you do that? Well, the centripetal acceleration of the moon is perpendicular to its velocity. Free fall, the acceleration of the apple in free fall is, the acceleration is down and the velocity is down. So they're parallel. But for the moon on a circular orbit, they're perpendicular. One is a centripetal acceleration. But Sir Isaac Newton said, I actually think they're the same force. One's acting on a celestial body, the moon, one on a terrestrial body, an apple, and other falling objects. So he could estimate the moon's centripetal acceleration. If he could get v and v squared, and if he can get the radius of the moon's orbit, then he can get, make a computation. Okay? So they knew the distance to the moon as a multiple of Earth's diameter or Earth's radius. Right? So they knew that. And it's about 60 times Earth's radius, roughly. And they knew what Earth's diameter was. And Sir Isaac Newton would have been working in feet and miles, not metric system. They didn't have that yet in Sir Isaac Newton's day. Plus they knew the circumference of the moon's orbit, fairly well. Not as well as, we know the distance to the moon now to nearest centimeter. It's pretty awesome if you think about it. But he knew it pretty good. And so they were able to figure out the circumference of the moon's orbit. Plus, they knew how long it took. So if you know how long it takes to go around a certain distance, you can figure out the speed, the speedometer setting of the moon, v squared over r. So he figured it all out. He put it all together, 9.8 meters per second squared for the apple. And what he found was that the acceleration of the moon wasn't very big. It was about 1/3600th of the apple's acceleration, g. And Sir Isaac Newton said, whoa, that 3,600, that's the square of 60. And the distance, the distance from the center of the earth to the apple in Sir Isaac Newton's backyard is, a certain number. It's about, 3,471 kilometers, I think is correct. Okay. And he knew that the distance all the way out from the center of Earth to center of the moon was about 60 times that, 60 Earth radii. And students, make a note, 3,600 and 60 radii, that is not a coincidence. Sir Isaac Newton said, I believe that that is the clue to the force law for universal gravitation. So let's take a look at that. He said, I think that there are only two factors, the mass of each object and their distance apart. As Sir Isaac Newton said, the more mass, the more force. Okay, so if you have the moon and the Earth attracting each other, you know, you have a certain amount of force. But if you have the Earth and a satellite, it's a smaller amount of force because the satellite has less mass. All right. He also said that the more distance, the weaker the force. And why did he know that? He knew that because the centripetal acceleration of the moon was so small. I mean, he got a fairly good value of it. And he said, you know, that's about 1/3600th of g that for the apple that fell on my coconut, you know, last week. And so he said, all right, I think that the force law is going to look like this. The quotient, M1 and M2, multiplied together, that's mass of one object, mass of the second object. All right? In the numerator. So the more mass you have in kilograms, the bigger your numerator. And he said, because of that 60 and 3,600 tip-off, I think that the distance is going to be in the denominator, and it's going to be the square of the distance. Not the first power, not the third power, not the 2.7 power, but exactly the r to the second power in the denominator. This is what we call an inverse r squared force. Now, capital G, you can make a note of that. That is a conversion factor. It's called Newton's constant or the gravitational constant. And he introduced it as a constant of proportionality. Kind of like when you, I don't know, you might remember from 6th grade science class or middle school science class, you know, when you convert from Celsius to Fahrenheit, you have a ratio 5/9 and 9/5 that you got to use. And you got to subtract 32 or add 32 and all that stuff. But anyways, that ratio 5/9, 9/5, I believe that's what it is. Yeah, 5/9 and 9/5. That's a conversion factor between Celsius and what this is, capital G, it's a numerical factor that he put in his formula so that the product of kilograms times kilograms divided by the square of a meter would give him newtons of force. So a newton of force has got to be kilogram meter per second squared. Now there's no seconds up there. There's no seconds squared. And there's kilogram in the numerator, but it's actually kilograms squared in the numerator. And the distance, the meters are downstairs, and it's the square of the distance. So you got to look. So he said, I've got to have to convert it to force. I've got to have a conversion factor, and he called it capital G for gravity, but we call it Newton's constant now, or the gravitational constant. And my wonderful students, in his day, he thought of it just as kind of a homely conversion device to convert his measurements of mass and distance into a force in newtons. But we now know that the size of G is actually involved with the size and intensity of black holes in Einstein's theory of relativity. And that's one of my research areas. And good old capital G, Newton's constant, is everywhere in the theory of black holes. And so it's kind of cool how that works. Anyways, this is the force law that all those PhDs in Hidden Figures were working with. it is not easy to work with because the distance is squared and it's in the denominator, so it's really tricky. The further out you get, the weaker it gets. So every ounce of rocket fuel gets more effective as you go up in the atmosphere, right? But you don't have as much, so it's a tough balancing thing. But I want to do some satellite examples with you, and what we're going to do with this is show you how the theory of universal gravitation, gm1 m2 over r squared, and the idea of centripetal force help us out with practical everyday satellite technology. All right, so let's think about the Earth, capital M for its mass, and a satellite, little m subscript s. So the Earth has a huge number of kilograms for mass, and a satellite might have a few thousand, big satellite, a few thousand, small satellite, a few kilograms, a few single kilograms. Okay, so there's a little wide range of those, but way smaller than the Earth. Okay, now the distance of the spacecraft orbit is set by NASA, and it's placed in orbit by rockets that NASA develops and fuels up with just the right amount of fuel and so forth. Okay, now if the spacecraft has a circular orbit, it's particularly easy to work with. It's not too bad for an elliptical orbit. You can work on it. But what we're going to concentrate on is a perfectly circular orbit. It's really easy to work out. Here we go. Okay. On the right is gravity. There's the law of universal gravitation on the left. And then over here on the right, there's the formula for centripetal force, mv squared over r. Now, m over here, this is the force on the satellite. And over here on the left side, the source of the force on the satellite is the gravitational interaction of Earth with the satellite. So the interaction is modeled with the mass of the Earth and the mass of the satellite in the numerator with good old capital G. And then the size of the circular orbit, it shows up in both sides. Okay, the radius of the orbit squared over on the left, first power, r in the denominator on the right. Right? Now, that's going to let us simplify things because there's some r's on the left, there's some r's on the right. And what we're going to do, before you fall asleep on me, we're going to try to get this simplified. Anybody see something that can cancel? Yeah, MS, mass of the satellite. Ching! And that, my wonderful students, is why the cannonball and the musket ball from the Tower of Pisa accelerate at the same rate. Doesn't matter how heavy the object is. Everything has a good old 9.8. Matter of fact, this number over here, capital G times the mass of the Earth divided by the radius of the surface of the Earth, that's equal to 9.8 meters per second squared. Pretty sweet. All right. Now, if you clean it up a little bit, you have GM over r squared on the left, and then v squared. So the only mass in here is really the mass of the Earth. Everything in orbit is it doesn't matter how big the satellite is, the spacecraft. Okay? So if you do a little bit of cleanup again, you get the r's, okay, get this r on the right and multiply it to the top of the left and then cancel. Now you just have 1 power of r in the denominator, and your formula is even simpler. Capital G, capital M over r equals v squared. And if you think about that, you have two factors that, that the the rocket scientists at NASA are going to worry about. The radius and the orbital speed, v. All right? So if you know the radius r for the orbit that you want, you can figure out the required speed and then design your rockets appropriately. All right? An example of that is a spy satellite. If you want it to be low enough, in other words, at a particular orbital radius, low enough to keep an eye on the Russians, yeah, you can do that. And if you figure out what altitude you have to have for your satellite, then you say, all right, that tells me what my orbital speed is. Now I can design my rockets and load them up with fuel and get it up there to the right orbit at the right speed. All right? The other way that you can do it is to say this. What if I need a certain orbital speed so that you can have a required altitude and a certain orbital speed which will control the orbital altitude and radius? Okay? In other words, what if you want a satellite that's fast enough to orbit the Earth once every day? Okay? Yeah, you can do that. You know, you can figure out the radius and the speed. And yeah, we can do that. One orbit per day, not a problem. Those are what we call geosynchronous satellites. Communication satellites. So if you have DirecTV or any of those dish antennas, all the TV stations use them. Yeah, they're using the satellites, and they're orbiting, but it looks like they're stationary. They're just kind of stationed. Your satellite dish, it's just aimed in one direction. It doesn't scan the skies, like a radar device, weather radar and stuff like that. It just looks in one direction, and it's always up there, if they have the right speed. So yeah, Gm1 m2 over r squared. It's known as an inverse r squared force. It is an infinite range force because of that. If you had r to the 2.5 power in the denominator, it wouldn't be infinite range. If you had r to the first power, it would not be infinite range. Now, proving that it's infinite range is pretty tough. You need a truckload of calculus. But I can tell you the conclusion that anything that has an r squared in the bottom for its force law, for F equals ma, infinite range. And so this is the force law that basically rules the cosmos. Electricity, the electromagnetic interaction is also infinite range. The problem with that is it can be screened. You can go into a building and lose cell phone reception. The electromagnetic field doesn't reach in there. Now, we're not done yet. I want to press just a little bit further here. A couple more comments. Almost done. The predictions of Edmund Halley, and this is particularly important. Your homework will involve this. Edmund Halley was a contemporary of Sir Isaac Newton. They were friends. And he applied the law of universal gravitation and figured out why it led to these three laws of planetary motion. Specifically, the third one, that the orbital average distance to the third power is proportional to the orbital period. All right? And that's down here. Here, little a, you don't have to worry about this formula. We're not going to calculate with it. But this is the formula that Edmund Halley developed. The mass of the two objects, the Earth and the satellite, or the comet and the sun. Here's the average orbital size, and capital P is the orbital period. And he said that comets follow elliptical orbits too, and therefore they would return periodically. And since they would be returning periodically, he should be able to predict them. So what he did was he looked at the comets of 1531, 1607, and 1682, and he said, that's one comet, and it's going to come back late in the year 1758. And by God, he was right. Christmas 1650. He was dead when Sir Isaac Newton was passed away. But yep, it came back. And it completely verified Newton's law of universal gravitation. Now, homework 7 is going to contain some additional reading about Edmund Halley and Sir Isaac Newton. It'll activate tomorrow, Friday. It'll be due on Tuesday. Okay, you're dismissed now. 11:51.